I forgot, so I set the camera so that it no longer turns itself off after 30 minutes. But now I can't tell when it's finished recording because it doesn't beep or anything. Because apparently the 30-minute limit on the recording is because the EU put taxes on video cameras, import taxes on video cameras. And they decided that it's a video camera if it can record for more than 30 minutes. So Canon put a limit on that it will only record for 30 minutes. You can apparently download Magic Lantern and get around that, but it voids the warranty. So we've missed like half an hour in high definition. So okay, how would you change this so that it didn't just print yes or no? It would print, if it printed true, it would be true or false. If it printed true, then it would also print an actual appetizer order. So how would we find out 7 times 43? So, okay, nobody's saying anything. So what you could do is say this is true, and then you have a little empty linked list. So true plus empty linked list. Or it doesn't have to be, it doesn't have to be a linked list, just some sort of, it can be a string or whatever. So then you can say, okay, if this is true, so we decide that we can make an order with price I by making an order with price I minus pj and then adding something of pj, then we can say, okay, AI is true plus, what am I going to put here? Well, abusing notation a bit, I'm going to put I minus pj's linked list with concatenated, which I'm going to draw as this symbol, plus j. Okay, so this, now if I see this is true, I can have it say, okay, if this is true, then if, okay, if A301, so if it's true, then print A301's list. Okay, do people see how that works? I have only 24 people. 23, possibly. If that 24 includes me. Okay, so you should be able to code it such that if I give you a particular number, then it will say yes or no. I mean, it actually only has to fill in the array once, but if I ask you, okay, can you get 292? Then it will say yes or no. And if I give you, and if it says yes, then you can print an array, an appetizer order that gives you that price. Okay, so I have about 20 minutes left, so I am not going to get through all the stuff I wanted to. So, what's weird about this? So you understand how this algorithm works. Let's look at how complicated it is. So if you're given some target number n, then you make an array of size 0 to n, so n plus 1, and then this loop this for I from 1 to n, this executes n times, and then in here this executes this inner loop for each execution. The outer loop, the inner loop executes as many times as there are prices. So okay, this is going to take, say there are m prices, this is going to take, well, this is an array lookup, and then this is just an assignment. So this is going to take something like n times m, right? Oh wait, that's still the answer. So n times m. So this is order nm. Right? People like that? It's okay? So, but think back to that cartoon we saw at the beginning. Right? Where it said embedding NP-complete problems in restaurant orders. NP-complete means it's hard. And I told you we don't have a polynomial time algorithm to answer knapsack. This cartoon was saying this is something like knapsack. Well, but here we have, this is quadratic, right? So this is a little bit subtle, okay? So on the one hand, we start out, I tell you it's hard, and then on the other hand, we just came up with a solution for it. And I wanted to make you code it, but we just kept going because we're running out of time. So what's the answer? I mean, is this a special case of that problem? And the answer is not really. But this, when we talk about hard problems and polynomial time, we mean polynomial time in the size of the input. So how big is this input, these numbers? Well, you'd say, well, it's like, what's the sense of the size of this? And you'd say, well, the size is like 301. And in order to teach you why that's wrong, I'm going to give you I'm going to sidetrack a little bit and talk about factoring. Okay, so people know this. Okay, good. I'm going to erase it. So factoring means given a number n, give me a list of its prime factors. Okay? So this is the basis, the difficulty of factoring. Maybe some of you have heard that factoring, it's not known to be NP complete. But it is believed that we don't have it's believed it's hard. Some people believe it's hard, some people don't. But we don't currently have a polynomial time algorithm for it. Okay? So if any of you have seen, there's a movie Sneakers with Robert Redford, River Phoenix, James Earl Jones, Ben Kingsley, Dan Aykroyd, and some other people from years ago. And it's about what would happen if somebody figured out a polynomial, a fast algorithm for factoring. Okay? And people are murdered, and the mathematician who finds it is killed, and all this kind of stuff. So now I made Alan find Huffman's algorithm. Now I'm going to make some poor person tell me an algorithm for factoring. Okay? So You can, yes, yeah, this isn't really dynamic. This isn't dynamic programming. This is easy. So, does somebody want to tell me how, if I give you a number n, I want you to tell me all of its prime factors. In fact, no, forget prime factor. I want to know all of its factors. Okay? And I want you to do that in time O of n. Is there anybody still there? I've lost even more people. Okay, so to keep things, to try to get back on track, no, I'm going to choose something. Yes, so it would be for I equals 1 to n, if n, let's not do that, let's put mod, I is 0, print I. And if n4. So, print statement, consider a constant time, modulus, consider a constant time. So this executes once per execution of the loop, and the loop executes n times. Yeah. But you don't have to. I mean, yeah, so what Liam's suggesting is basically the sieve of Aristophanes. But in this case, I just said O of n time. This will do it. Okay? So I mean, they made movies about, spies killing each other to try to get a fast algorithm for factoring, and here, Gabriel and Riz, Liam are saying, yeah, we can do it quickly. Okay, so what gives? Okay, what's the weirdness here? And the weirdness is, here we're talking about a number n, okay? But what is the size of your input? Well, it's not really n, okay? Because if I write the number 7143279, okay? How big is what's actually being passed to the program? Well, it's a number, it's 1, 2, 3, 4, 5, 6, 7 digits. Okay? So now, if I add another 7 digits, 8, 2, 3, 4, 6, 1, 5. So the size of this input measured looked at as a string has only doubled. But this number got a lot bigger. Okay? So basically, if you double the number of digits, you sort of square the number. Square the maximum value of the number. So you go from being bounded by 10 to the 7 to being bounded by 10 to the 14. Okay, so if you look at if you're measuring the input as sort of this as the number, then yes, we can do this in polynomial time. But if you look at it as the size of the number, then we don't have a polynomial time algorithm for it. So basically, what people want when they say we want a polynomial time algorithm for factoring, what they mean is we want something polynomial in the size of the logarithm of the number. And that we don't have. So the same thing, when we did this array from 0 to 301, that's taking, that size of that array is linear in the number, in the target number, but it's not, but that is exponential in the number of digits in the number. Okay? So this is tricky. Now there are some problems. So for example, if we took factoring and we didn't express the input number in decimal or in binary, if we expressed it in unary, so in unary the number 7 is just 1, 1, 1, 1, 1, 1, 1. That's 7 in unary. So then, in unary, the size of the representation of a number is the same as the number. So if the input to your program, to your factoring program, if the input is expressed in unary, then yes, it will run in basically linear time. As long as you sort of convert and then actually do the math in binary. Okay, sneakers is not, I like it, but for example, you've probably heard of quantum computing. One of the reasons why people have been hunting for quantum computers, maybe not the main reason anymore, but one of the reasons it sort of quantum computing sort of got started a long time ago was that a guy called Peter Shor found an algorithm, polynomial in the size of the logarithm of the number, for factoring integers on a quantum computer. So Shor's algorithm is still, if you ask, well, what could you do with a quantum computer? Now people say we can simulate quantum systems and stuff like that. But it used to be that if you said, what can you do on a quantum computer that you can't do on a classical computer, people would say, well, you can factor by Shor's algorithm. So there are problems where even if you express the input in unary, it remains hard. Okay, we still don't have a polynomial time algorithm for it. For example, if you think of tree coloring, if you express all of the numbers in unary, well, each vertex, you could write all the adjacency lists by writing each edge is represented as a number. So you've got the vertices from, say, 1 to n, and then you've got numbers from 1 to n. So if you now write these numbers in unary, well, you expand by n, but your input was already of size at least n. So you're at most squaring the size of the input. And if you square the size of the input, then the running time of your algorithm is allowed to be like, if it's bounded by a polynomial in the square, then it's still bounded by a polynomial in the size of the original input. Okay, so this is why we have this inconsistency. Why you read that cartoon and you think, yeah, but didn't Travis teach us an algorithm for knapsack? So you can modify that algorithm so you have to use a two-dimensional array. You can modify the algorithm such that it only uses one of each appetizer, and this is more in line with the original knapsack problem, because then you have an item and then you can take it or you can leave it. But just because you take it, it doesn't mean you can take another one. Maybe you don't have an infinite supply of each item. Okay, now this is where I this is going to be scribe notes for one group. I want to give you another example of something you can do with dynamic programming. And that's maximum sum subarray. So people are leaving, but this is interesting. Uninteresting part. Okay, so I have to do this in like 6 minutes. You can do max sum subarray with dynamic programming, because what do you do? Well, suppose you have the input array, which is called, what was it called? Nums? Yeah, let's say it's called nums. And it was from 0 to num size minus 1. Okay, so now, to do this with dynamic programming, what we're going to do is say we're going to have an array A, which is also going to go from 0 to num size minus 1. And I want it such that AI is the sum of the max subarray and I want this max subarray of length greater than or equal to 1, okay? That ends at, so this is max subarray in nums at nums I. Okay? I'm giving this whole lecture to like 20-something people out of a class of 111. Okay, but at least it's recording through my crappy webcam. Okay, so this means if there's a maximum sum subarray, it ends somewhere. So if we can fill this in from A0 to A num size minus 1, then we can just skim over this and look what the maximum number is and say, okay, that's the maximum sum of any subarray that ends anywhere, so we return that number. Okay? So, how does this work? Well, AI, suppose we filled in from AI, from A0 to AI minus 1. We filled all of those in, and now we want to fill in AI. Sorry if this is hard to read. So what can we do? Well, we have to take AI, okay? So what are the two cases? And I'm running out of time. Okay, before we get to 12:55, I'm going to tell you, I'd like you to actually code this. And then, as a dynamic program, and then I want you to run it on LeetCode to solve the max sum subarray problem. Okay? And then, once you've got that working, it works in linear time. So remember, our divide and conquer algorithm was n log n. And when we were talking about reductions, I said that, look, you can reduce max sum subarray to max sum circular subarray in linear time and backward and vice versa. So that means if somebody gives you a linear time solution to max sum subarray, you automatically get a linear time solution to max sum subarray in a circular array, also in linear time. Why? Because if somebody gives you an instance of max sum subarray in a circular array, you take it, turn it into two instances of max sum subarray, solve each of those in linear time. you turn it into two instances in linear time, solve them in linear time. They don't get bigger. Okay, you solve them in linear time, and that gives you the answer for your max sum subarray in a circular array. Okay, yay reductions. So once you've figured out, I would tell you, but it's not hard, and I have 1 minute left. This is not how you get AI. Well, I don't have time to write. You look at AI minus 1. If this is positive, then you can get more by taking whatever ended here and this. But if this is 0 or negative, then you just take this. Okay? So it's AI. If AI minus 1 is positive, then AI is AI minus 1 plus nums I. And otherwise, if AI minus 1 is 0 and negative, then AI is just nums I plus nothing. Okay, implement that, get it going on LeetCode, and then use that solution to solve that other problem on LeetCode, max sum subarray in a circular array, because that way, just take your code, do not change it, just take it and paste it in as a subroutine, and then call it twice, right? Because that way you get practice on dynamic programming, and you get practice seeing on reductions, which is going to help you when we get to NP completeness. And I'm out of time. So again, I'm sorry that we lost a lot of time fighting with technology, and I will try to have the new webcam working for Wednesday. Possibly I will end up running this through Zoom or something. Questions? People are just leaving. Oh, okay, good. Everyone understands. I'm sorry about really, I would have tried it, but I literally got back right before the class. Okay, so when you say does it need to be done, you're given this as the input. So you're given, remember, it's like something like you're given something like void max subarray, and this takes int pointer nums and int num size and returns, and now you do this whatever, and then you print or return. Yes, but then you're overwriting your input, which is a side effect. Oh, so yeah, if you want to actually return this, then you can do the same trick where if this, in addition to the number, it's also storing a list of the values. Well, actually, you don't need a list of the values because it's a continuous range. So if it stores the starting point, right? So if it stores the starting point of this max sum array that ends here, max sum subarray that ends here, this, if this is positive, this takes its starting point, and if this is 0 or negative, this says its starting point is I. If you want to return the contents of the max subarray, then yes, you better keep this lying around. But in general, it's unless somebody has told you, you actually get to use the space for the nums array, because remember, it's being passed as a pointer, which means you've all seen this call by